Now that we have the definition of singular value decomposition at our disposal, let's look at some of the properties of singular value decomposition. So remember, singular value decomposition arises as a matrix factorization. We can take any m by n matrix A with rank R and write it as the product U times sigma times V conjugate transpose, where U and V are matrices with orthonormal columns, and sigma is a diagonal matrix whose diagonal consists of positive numbers listed in decreasing order. So if we are given a singular value decomposition that looks like this, it turns out that the columns of U and V are related to one another via the following formulas. If we take our matrix A and we multiply by the jth column of V, this is guaranteed to equal the jth singular value multiplied by the jth column of U. On the other hand, if we take the jth column of U and multiply by the conjugate transpose of A, this is guaranteed to equal the jth singular value of the matrix multiplied by the jth column of V. So here what we're looking at are formulas we get that relate the columns of U and V to the matrix A and its singular values. These equations look a lot like the equations that define eigenvalues, but here the context is very different because we are studying general matrices, not just square matrices. Another thing that pops out of this observation is that if we know a singular value decomposition of a matrix A, we get a singular value decomposition of its conjugate transpose for free. If A is U times sigma times V conjugate transpose, then A star is equal to V times sigma times U conjugate transpose. So let's look at an example here. So here we have the example from a few slides ago where we take our 2 by 3 matrix with rank 2 and express it as the product of a 2 by 2 matrix U with orthonormal columns, with a 2 by 2 diagonal matrix whose diagonal entries are 5 and 3, multiplied by a 3 by 2, the conjugate transpose of a 3 by 2 matrix with orthonormal columns called V. Well, we can verify ourselves that the columns of U and V are related by the formulas from the previous slide. If we take our matrix A and we multiply by the first column of V, which here would be the first row of V conjugate transpose, 1 over root 2, 1 over root 2, 0, this is the same thing as 5 multiplied by the first column of U. If we take A and multiply by the second column of V, we produce 3, which is the second singular value, multiplied by the second column of U. Then if we take the conjugate transpose of A and multiply by the first column of U, we produce the first singular value, 5, multiplied by the first column of V. And then if we take the conjugate transpose of A and multiply by the second column of U, we produce the second singular value multiplied by the second column of V. So here we just have an example illustrating that the formulas we just gave actually work. What else can we say about singular value decomposition? Well, it turns out that if we have a singular value decomposition, A equals U times sigma times V conjugate transpose, the data in this factorization is actually convenient for solving problems involving A. Our first result in this direction says that the columns of U form an orthonormal basis of the column space of A. One consequence of this theorem is a corollary which we could state, which says that the columns of V form an orthonormal basis of the column space of the conjugate transpose of A. This is because when we take the conjugate transpose of A and we have our original singular value decomposition, we get the singular value decomposition V times sigma times U conjugate transpose. So what does this do for us? Well, if we are given our singular value decomposition, so here we have our 2 by 3 and its singular value decomposition, this automatically gives us orthonormal bases of the column space of A and the column space of A conjugate transpose. the column space of A has an orthonormal basis given by the columns of U. So here the column space of A is the same as the column space of U, but the idea is that U has orthonormal columns, so this basis is maybe more convenient to work with. Same goes for A star. The column space of A star is the same thing as the column space of V, but V is a more desirable matrix to work with because its columns are orthonormal. We can also use singular value decomposition to solve projection problems onto any one of the four fundamental subspaces. Let's say we have a singular value decomposition, A equals U times sigma times V conjugate transpose. It turns out that we can project onto any one of the four fundamental subspaces using this data. Projection onto the column space of our matrix is given by U times U star. Projection onto the column space of A star is given by V times V star. And because of the orthogonality relations, we therefore then know that projection onto the null space of A star is the same thing as the identity minus projection onto the column space, U times U star. And projection onto the null space is the same thing as the identity minus projection onto the column space of A star, which is V times V star. So if we are given a singular value decomposition, we can calculate our projection matrices quite quickly. So let's look at an example here. Again, we have our 2x3 matrix and its singular value decomposition. Let's say we wanted to project onto the column space of A star. Well, our theorem from the previous slide says this is the same thing as V multiplied by V star. So when we take our matrix V and multiply it by V star and multiply everything together, we get projection onto the column space of A star, which is this 3x3 real symmetric matrix on the left here. So again, we don't have to do any complicated arithmetic here, and we don't have to invert any Gramians. We just simply multiply V by V star, and we get projection onto the column space of the conjugate transpose of A.